we should be live, and we should have some audio. Everything should be working, right? Right? Technology. There we go. I'm live with audio. Okay. Somebody last week commented that the unedited hidden QA was very rambly and I should get to the point and be better organized. I thought that was really funny because like the whole point of this show is that it is disorganized and rambly, and we turn this into the edited, highly polished QA. Like, how did you even find it? We hide it. So, anyway, if you don't know what it is that you have stumbled into, this is the raw material. This is the grist for the mill that turns into my weekly questions and answers show. And you folks here hanging out today, you get to ask me questions live, and I will answer them live. I have no idea what it is that you intend to ask me, which is great because it's super fun. Nothing sharpens the mind than having to have all of human knowledge, space and astronomy knowledge, in your head at the same time. Nancy is off tonight. She is sick. So we've got Chad. Everything's fine, but she just is feeling, not up for it tonight. So, but we got Chad, and which is helpful because he then has to edit this episode afterwards. But yeah, go ahead and post your questions. Now, if I don't answer your question in the show, there's a couple of reasons. One is I try to put emphasis towards people who have never had a question answered before. I want to try and share the love to everybody. So I can tell how many questions you've asked, and I try to get the people who've never had a question answered because I think that's fun. I may answer the question because I may not answer your question because I don't know the answer. Maybe your question has math or is like very esoteric. There's a lot of great questions that I look at and go, man, if I was a gravitational wave astronomer who understood relativity at that level, I sure could give you a good answer, but I can't. I'm just a fancy science monkey. Yeah. And then maybe that it's a question that I've answered a whole bunch of times recently, so I may avoid the question if that's the case. But let's get into this week's question show. So I'm going to start the recording. Oh, and Chad, have you had a chance to edit last night? Did that method of me posting the question afterwards or reading the intro at the end of the show, did that work for you? Do you want me to do that? It worked. I'll do that again. Just try to remind me. All right. Recording video. Recording audio. Let's get into it. Oh, and I've got the winning question for last week. Okay, here we go. All right. Let's see. Okay. Hey everyone, welcome to another question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I'll answer them here. We record the show live every Monday at 5 p.m. Pacific time. So if you want to participate in the live show, ask your questions live, get answers, chat with the rest of the people, definitely come and watch the show with us live. Now, you're going to see some planet names show up above my shoulder. This shoulder, but maybe this shoulder. I just covered all my bases. And that is, of course, a way for you to vote on which question you thought was the best, or maybe which answer you thought was, or the question-answer combination that you liked the best. So definitely go ahead and give a vote. I see a lot of people just like asking a question. They don't vote. How will we know what are good questions if you don't vote? And then we can celebrate. Speaking of celebrations, Last time we had the winning question was from J Cross. How many Oort clouds will we pass through when Andromeda M31 passes through the Milky Way? That got the most votes. So congratulations to Jay and congratulations to Jay and congratulations to me for answering the question. We did it, Jay. All right, let's get into this week's questions. Will I run for president in 2024 or beyond? I can't. I'm Canadian. Canadians can't run for American president. Or can we? I can run for prime minister. All right, here we go. So remember, I've got a bunch of prepared questions first, and then we'll get into your questions. Yes, I am recording. Violin Girl 79. How far would you have to travel before your view of the constellations began to significantly shift? If you answer my... Actually, no, I'm not going to do the other part. All right. The constellations that we see in the sky, and there are 88 constellations, plus a whole bunch of asterisms like the Big Dipper or the Coat Hanger cluster, they are collections of stars from our perspective here in the Milky Way. And in fact, you wouldn't have to go very far for the constellations to start to warp and change and eventually become completely unknown to you. So I'll give you some examples. One constellation is Ursa Major, and the Big Dipper, which is an asterism in the Big Dipper. I know it's a sort of a weird term. The Big Dipper isn't a constellation. Ursa Major is a constellation. It's a collection of stars in the sky that sort of seem like a grouping. And the Big Dipper, the closest star in the Big Dipper is Mizar, which is 78 light years away. And the most distant star in the Big Dipper is Dubhe at 124 light years away. And so those stars are actually pretty close to each other. You could travel towards the Big Dipper for quite a while, and it would look like the Big Dipper. It was only once you got past 80 light years that now suddenly stars would be on the opposite side of you. But you could fly sideways, and the Big Dipper would look completely different. So in the case of the Big Dipper, I would say that if you flew about 100 light years away from Earth, it would no longer be recognizable. There'd be some stars that were on one side of the sky and other stars that were on the other side of the sky. But a constellation that is much farther than that is Orion. And we think about Orion, we've got those familiar shoulders, Betelgeuse, we've got the belt. But the closest star in Orion is 243 light years away, but the most distant star is 1,360 light years away. So in fact, Orion is stretched out into this long string of stars that you would have to fly past one after the other. But obviously, once you get to the halfway point, many of the stars are going to be on one side of you, many are going to be on the other side of you. So Orion will start to fall apart as you fly towards the most distant star. And it's kind of incredible to think, when you think about the actual scale of the Milky Way, we are about 28,000 light years away from the center of the Milky Way, a similar distance to the rim of the Milky Way. And so you could go to any number of places around the Milky Way, and you would see completely different constellations in the sky. There's almost like no, I think that's finished. Do you want to conclude that in some way? So I would say that if you traveled more than 10 to 20 light years away, the night sky would start to change pretty dramatically. A lot of the brightest stars would no longer be on the same side of the sky, and after a while, all the constellations would start to fall apart as you got a few hundred light years away from Earth. Audrey Mayer. In the last video, you talked about how JWST is being able to see almost to the edge of the observable universe. So I was wondering, is there any possible way to see beyond that, or at least to understand that better? So let's think about the universe. And of course, the universe as we see it out there, as we look farther away from the Earth, we are seeing further back in time. And so we can never see the universe as it looks today. We can only see the universe as it looks in the past. If time was no issue, if we could fly an infinite amount of faster than the speed of light, then we could travel to any spot in the universe and it would look kind of similar to what it does today. There'd be galaxies, there'd be stars, there'd be white dwarfs, black holes. It would look roughly similar. It's only when we look farther away are we actually starting to get a sense of what the universe used to look like. And when we think about the sort of the shells, right? And in the news segment that I did a couple of weeks ago, I talked about how for the first, say, and it's important to note here that we don't really want to talk about distance in the universe because the universe is expanding. Objects that release their light are no longer at the distance that we see them today. It's most important to just talk about the amount of time it took light to get us. So if I say that light has been traveling since the beginning of the universe 13.8 billion years ago, that light has left a place that was 46 billion light years away. I know it's very complicated. The light is moving, we're moving, the universe is expanding, and so distances and times don't really work the same way. But if you got, say, about 1 billion light years away, right, you would be seeing, I'm going to do this a different way. Okay. So with JWST, it can see all the way back to about 200 million years after the Big Bang. And the only reason that it can see that far is because that's when the first galaxies were starting to form in the universe. And they were bright enough that JWST should be able to resolve them. And in fact, just like this week, we got a great press release talking about how they've been mapping out galaxies at about 200 million years after the Big Bang. So theoretically, like if you had an object that was as bright as an early galaxy, then JWST could see farther. But so far, there aren't any of these bright objects. Like the first bright objects are these first galaxies. Now, there are other things that are farther than that. They're just fainter. So if you could see to say 100 million years after the Big Bang or 50 million years after the Big Bang, then you would start to see the first stars in the universe as they were forming. They would be big, massive, pure hydrogen and helium, but on an individual star-by-star basis, they don't compare to the brightness of an entire galaxy. So JWST just can't see them. Now, there have been thoughts that you could build a more powerful telescope than JWST. There was considered a telescope that would come after JWST called Origins, and it would be about a 12 to 15 meter telescope that was a far infrared like Origins would be a, say, 12 to 15 meter telescope that would be, actually wasn't going to be that far. Let's say 10. I think it was like 10. All right. Origins would be a far infrared telescope like JWST, but it would be larger, like maybe 10 meters across. And it would be sensitive enough to see those first stars forming. And so now we could say, well, now we've got a telescope with the Origin Space Telescope that's capable of seeing the universe as it looked 50 million years after the Big Bang or 100 million years after the Big Bang. And we can actually watch those first stars coming together. But then before that, there were no stars. There was no source of illumination. And so you just can't see that. But there is a type of radiation that was before those first stars. And this is called neutral hydrogen. Essentially, after the Big Bang, you've got all of the universe filled with all of this hydrogen. And hydrogen, over long periods of time, will release a very specific wavelength of radiation. It's called the 21 centimeter line. The gist is that if you detect the photons of this radiation, that tells you where giant clouds of hydrogen are. And actually, new radio telescopes like the Square Kilometer Array are being built. And one of the jobs that they're going to do is to search for this signal of hydrogen being released after the Big Bang. And this might take you right up to the edge of the cosmic microwave background radiation. That's the next line, which is the cosmic microwave background. That is light that was released when the universe first became transparent. And that is about 300,000 years after the Big Bang. And we can't see before that, even though we know that there was 300,000 years before the cosmic microwave background radiation was released, we have no way to be able to probe it. We have no way to probe it. Let's see. Even though we know that light was released about 300,000 years after the Big Bang, we have no way to probe it in the electromagnetic spectrum. But in neutrinos or in gravitational waves, both of those were able to be released before the universe had become transparent. And in theory, there would be neutrinos and gravitational waves released right back to the very beginning of the universe, so that full 13.8 billion years ago. And so once next generation gravitational wave observatories come online, when next generation neutrino observatories come online, we should be able to observe until minutes, seconds, tenths of a second after the Big Bang. Can we go beyond that? Probably not. The very fundamental forces of nature as we understand them were created at those first moments at the Big Bang. Now, it's possible that there was something before the Big Bang, and that might leave some kind of imprint in the current Big Bang, but you wouldn't be able to observe it. You would just be able to detect this echo from whatever was the previous universe. And astronomers have considered that that might be a possibility. So right now, the JWST's limit is about 200 million years after the Big Bang. The cosmic microwave background is about 300,000 years after the Big Bang. And new technologies may be able to take us right to the very beginning of the universe. Cynicus. If the Big Bang was more energetic than any other explosion, why couldn't many metals heavier than lithium be formed like we see with heavy metal fusion in neutron star mergers? So back at the very beginning of the universe, when the universe was hotter and denser, there was a time when the entire universe was kind of like the inside of a star, the core of a star. So that period started about 20 seconds after the Big Bang, and it ran until about 20 minutes after the Bang. So really just for 20 minutes at the very beginning of the universe, the entire universe, everything everywhere, was so hot and so dense, it was like the core of a star. And just like a star, you get hydrogen being fused into helium. And in some cases, other elements like lithium and beryllium, and maybe some trace other elements. And then once the universe had grown and gotten cooler and gotten less dense, then the temperature and the pressure dropped to the point that this fusion would no longer continue. And so the amount of hydrogen versus helium versus lithium were locked into place for the rest of the universe. I mean, obviously, we've got more various elements being formed afterwards in stars and so on, but just like the baseline raw material for the entire universe was defined in those first 20 minutes, which is pretty amazing. To get elements that are higher up the periodic table than hydrogen, helium, lithium, etc., you would need to have a region that is more dense. But the thing is that when the universe started, it cooled down to the point that the first atoms could even form, and then those atoms turned into the hydrogen and the universe from the beginning in those first 20 seconds had cooled down to the point that like the fundamental forces formed. And then you got the first protons, and those protons started to fuse into helium and lithium, etc. And then the pressure cooled down. And from that point, it's never been dense enough and hot enough across the entire universe to form heavier elements. But when you think about the forces involved in two neutron stars colliding, like you've got these two objects with the entire mass of multiple stars crashing together. And in that moment, the energies involved are just astronomical. And you've already got protons to work with. Like the protons didn't have to form out of the universe itself. You've got protons, and now you can start mashing them together. And so the levels of energy that come with colliding neutron stars, with exploding supernova and things like that, are just the only places now where we can get those most heavy elements in the universe. So those are the prepared questions. Let's see. Let me get the answer. QZY123. What is the shortest duration event that Vera Rubin will likely be able to capture, and what will it miss? Are there other surveying observatories in the pipeline that will shorten that span? So the Vera Rubin Observatory, of course, this is the telescope that I'm probably the most excited about, and this is going to be built in the southern hemisphere in Chile, and it has this really wide field of view. And every few seconds, it's going to take another picture of the night sky at a level of depth that rivals the capability of other observatories that we have on Earth. It has the largest digital camera that has ever been made, and it will be able to capture very faint objects very quickly. And every about 2 nights, Vera Rubin will scan the entire sky that it has accessible to it in the southern hemisphere, and then it'll start all over again and start scanning the sky again. So what kinds of objects will it see? Well, it'll definitely be able to see an asteroid, a faint asteroid, as it is moving through a patch of the sky. It may see like the asteroid in one location, and then when it comes back 2 days later, a different picture will show that asteroid, and they'll be able to see the movement between those two areas. With a supernova, it will be able to detect the supernova, and then through the afterglow. So when a supernova goes off, you get this afterglow in the sky that can last for days, weeks, sometimes even longer. And it will definitely be able to detect those. Variable stars can change in brightness over the course of days or maybe even weeks, so it's definitely going to find those. Eclipsing binaries, where stars are passing in front of each other. But you can imagine a range of objects, and I think this is what I'm most excited about Vera Rubin, is that there are going to be events that happen in the universe that astronomers have ever known. There are going to be events in the universe that astronomers have never seen because they've never been looking at the same patches in the sky so quickly with this kind of cadence. You can imagine some event that maybe lasts an hour and fades away. And so what would it take for you to be able to see that? Well, if Vera Rubin doesn't come back for another 2 days to be able to observe that same spot, then it won't be in the first image. 2 days, it will have happened for an hour, and then 2 days later you come back and it's not there either, and so you miss it. But if you capture enough pictures of the night sky, you're going to suddenly start to notice these objects with a very specific signature in some of your images. And then after a while, that's going to give you a sense that these things are out there. So it's really hard to understate how important and how exciting this telescope is. I mean, is there anything that will shorten that span? Not that I know of. We have a similar system in the north called the Zwicky Transient Facility, and this was the object that discovered that asteroid that crashed into Canada about 2 weeks ago. But it's nowhere near as sensitive as what Vera Rubin is going to be. I think the big thing that's missing is a Vera Rubin North. So you have one that's covering the northern hemisphere and one that's covering the southern hemisphere. And then space-based telescopes. But I haven't seen any plans to build space-based versions of these. But I really think this time domain astronomy is the next really exciting frontier of astronomy. And Vera Rubin is going to open our eyes to a universe that has been doing a lot of things while we weren't looking, and now we're looking. YouTube Joseph WM. Fraser, can do live streams with famous astronomers and planetary scientists that I know from shows like Greg Laughlin or Dan Durda. I've talked to Dan Durda in the past. I mean, I've probably interviewed 300 people. I've interviewed NASA administrators, astronauts. I've interviewed probably most of the people that you know of on the History Channel. I've interviewed everybody, and if I haven't, I just haven't gotten around to it. I've interviewed Man, so many people. And to be honest, I much prefer interviewing people that you've never heard of. I think that the people who you see on the History Channel and Science Channel and things like that, they've turned into science popularizers. I mean, they're still scientists. I mean, Dan Dirt is a terrific scientist, but they've also turned into science popularizers, communicators. And I really enjoy finding the people who are doing really good research who never talk on media, but they're very well spoken and they're very interesting to talk to. And they don't know how to manage their media presence. And so I can just talk to them about whatever is occurring to me, and I'm not going to get some standard. Like if you look at the interview I did with Michio Kaku, it was fascinating, but he has given these answers so many times that it's just not super interesting to me. I'd rather somebody who is working on really interesting work that you've never heard of. And you have to just trust me, right? Like you got to trust my judgment that I'm going to find people who are doing interesting work that is of value for you to listen to. And don't worry too much about whether or not, I'm not doing fan service here. I'm trying to push the limits of our collective understanding. And you're going to have to just trust me. It's like going into a restaurant and trusting in the chef to make you a dish. Trust me, I'll make you a tasty dish. Series K. Lee, did you see that NASA might release JWST immediately? Scientific American is against it. I did see this op-ed. In fact, I saw. Okay. So the op-ed that you're talking about is actually written by Jason Wright, who's like one of my favorite astronomers. I've interviewed him in the past. He is both an exoplanet astronomer, a professor, a mentor to many other astronomers, and one of the coolest people thinking about extraterrestrials, technosignatures, things like that. And he makes some very good points about why to not release JWST data right away. The problem is getting scooped that if you, I should probably explain, maybe you can put this in, Chad, later or at the beginning. The way JWST and most observatories work at this point is that if you're a scientist and you book time on the telescope, that when the data returns to you, you have a proprietary time period that you can work with that data, do your peer review, cross-reference your research with other observatories, and publish your paper, and then you have made the discovery. And that process makes a ton of sense because it takes time for you to be able to do this research. But if the data from the telescope is just dumped out onto the internet immediately, the moment that you do your research, that now you're in a race with other researchers. And even though you have booked the time on, say, the TRAPPIST-1 system looking for a planet in the habitable zone, the moment your data is out there, you've got 100 astronomers hungry to scoop you on the results. And then now the race is on. And what that means is that now no longer is it are you under pressure to get the science right? You're under the pressure to get the science out first. Whoever gets the science out first is the winner, even if it's bad science. And that's a bad incentive. So I am fine with there being a proprietary period where the people who have actually proposed the science in the first place get a chance to work with the research. Just right. So, and I think that a lot of the research that's being done, or I think that actually a lot of work is being now done in large survey telescope missions. I mentioned Vera Rubin, there's Gaia, the Zwicky Transient Facility. There are a lot of these big surveys that are scanning the entire sky and they're just dumping this data into databases that then astronomers are looking through to get answers. You don't book time on a telescope, you just dig through the data. And I think that's the right way, that to have more of these survey missions as opposed to individual telescopes. Like I would rather something that is the equivalent of JWST, that is scanning the sky at not quite as good as JWST, but is scanning a vast volume of the sky and dumping it onto the internet. Kind of like the Nancy Grace Roman mission, which is going to be able to see, kind of like the Nancy Grace Roman telescope, which is going to be able to see large amounts of the sky night after night, although it's in space. Is it really night after night? Anyway, you get what I'm saying. So surveys over dedicated observatories. But at the end of the day, if you are a scientist and you propose time on the telescope, then you should have at least a few months to get a head start on other people who are going to try and scoop your results. And I think if the data is released and it starts to turn into bad science because everyone's in a rush to publish first, then we know that they've gone down the wrong path. KB. How far out can we see that is in the present-ish? I get what you're saying, the present-ish. So obviously, when we look out into space, we are looking backwards in time. And so when we see the moon, we're seeing the moon as it looked a couple of seconds ago. When we look at the sun, we're seeing as it looked 8 minutes ago. When we look at Pluto, we're seeing as it several hours ago. When we look at Alpha Centauri, we're seeing it about 4.5 years ago, et cetera, et cetera. So when I think about your question, like what is present-ish, I think like what is a similar form and structure to what it is today. Like when we look at Andromeda, we're looking at a galaxy that is 2.5 million light years away. We are seeing Andromeda as it looked 2.5 million years ago. But the reality is that if you could blink over there and look at it, it would look essentially identical. Some of the stars would now be a few million years old, but stars last billions of years, so it's not a big deal. Some stars will be gone, some stars will be born, but roughly it's going to look the same. And as we look out into the universe with big telescopes, we can see these giant spiral galaxies out to a couple of billion years. We can see these giant spiral galaxies out to a couple of billion light years away from us. Or I guess the light has been traveling for a couple of billion years, but you get what I'm saying. Then, beyond that, we're unable to see the big spiral galaxies, and now we can mostly see the elliptical galaxies, which are brighter, but they're also, in many cases, older. They've run out of major star formation, the result of spiral galaxies crashing together. Beyond that, we can only really see galaxies because they have a quasar in them. And quasars are things that happened several billion years ago, but they don't really happen so much anymore. I mean, maybe the Milky Way will turn into a quasar when it merges with Andromeda, maybe not. So I would say a couple of billion light years away from us is roughly in the present-ish. And beyond that, you're starting to see an era of the universe that just no longer exists anymore. And like when we think about, say, about 3 billion years after the Big Bang, that's considered cosmic noon, time when there was the maximum amount of star formation in the universe. Right now, the Milky Way is only forming a new star every year or so, but imagine a time when the Milky Way was forming a star every day. Like, star formation was vastly more active back then than it is now, and it was a very different universe, kind of like walking around the dinosaur age was a very different Earth than it is today. So a couple billion years. Max 410 Berry. What books or textbooks would be good to start learning more astronomy? It really depends on what you want to get out of this. Like, are you just wanting to just like immerse yourself in astronomy knowledge and just kind of enjoy the ride? Then I think you can be fairly casual about that. I really like the Crash Course Astronomy that's done by Phil Plait on YouTube. Obviously, we do Astronomy Cast. We're up to 660 plus episodes where I'm interviewing a PhD astronomer week after week after week. And so after a while, I think all the knowledge will start to build up in your brain. Now, if you want to follow a more formal approach, but without actually going back to university, many universities offer their full courses online. The best example of this is like MIT. MIT has you can take an entire astronomy or physics degree, course by course, accessing the textbooks, or buying the textbooks in some cases, but getting the list of the reading material, the problem questions, even watching the lectures in some cases. And if you're a self-starter, you can go through this entire process and walk out the other side with the same knowledge as somebody who actually attended these classes and got their undergraduate degree. You just don't get the piece of paper. But like, does that really matter, right? Like, don't you just want the knowledge? Isn't that what going to university is for? Is to just fill your brain with knowledge? Or is it to get a piece of paper so you can get jobs? I don't know. Anyway, so you can in a more structured, formal way. I also like the great courses. They have some great, again, lectures by astronomers. And then as you're more advanced, the thing that I recommend is to go back to YouTube and start looking for topics that you enjoy, but you can actually change the search criteria to look for things that are, say, over an hour long. And if you do things like gravitational lensing and then lecture, then you can see someone from a university giving a lecture on gravitational lensing to graduate students, and you can watch it and mostly understand what they're talking about. So I think the internet is amazing, and you can fine tune the kind of information that you want and then what you're ready for. But the way that I like is to find some podcasts that you really enjoy. Daniel and Jorge Explain the Universe. Daniel and Jorge Explain the Universe is fantastic. There's a lot of really great podcasts, and you just listen to them week after week after week. And after a while, the knowledge just starts to get into your brain, and you can start to look at papers or journal articles or news results and understand them better. Or just keep watching my channel, and after a while, it'll all start to sink in. This great course is called Wondrium. Okay. Snars. Is there another interstellar object heading Earth's way? Inevitably. There are probably 30,000 interstellar objects passing through the solar system right now. DD, are rockets with eternally reusable fuel possible, or a fuel source that can be recycled all the time or used over and over possible, that we can really have eternally traveling rocket? No. I'll answer this one. DD, are rockets with eternally reusable fuel possible, or a fuel source that can be recycled all the time and can be reused over and over possible? That way we can have an eternally traveling rocket. Wouldn't that be amazing? In rocketry, you have the tyranny of the rocket equation. And the gist of this is that if you want to move your rocket, if you want to fly towards some destination, the only way that you can do it is to hurl something overboard. You have to throw something off of your rocket at high velocity. And thanks to Newton's third law, for every action, there's an equal and opposite reaction. When you throw stuff out of the box, thanks to Newton's third law, right, for every action, there's an equal and opposite reaction. As you throw things out of the back of your rocket gets a kick in the opposite direction. The faster you can throw them, the heavier these things are, the faster your rocket will go. But eventually you run out of things to throw out of the back of your rocket, and then your rocket is now just coasting forever. So all of the ideas in rocket propulsion are just different versions of throwing things overboard at different velocities. A chemical rocket, obviously, you have some chemical reaction and you fire exhaust gases out the rocket at high velocity, your rocket's kicking in the opposite direction. An ion engine, you are hurling ions out of the back of the rocket. They're with an ion engine, you have with an ion engine, you are hurling ions with electricity out of the back of your spacecraft, and it's getting a kick in the opposite direction. With a nuclear rocket, you are running a nuclear reaction in the rocket. You're then heating up some kind of exhaust gas, and then you're blasting that out the back. Like all of them. A fusion rocket, same thing. Even an antimatter rocket, you are mixing matter with antimatter. You are creating energy that is allowing you to throw some exhaust mass out of the back, and your rocket is getting a kick in the opposite direction. Even a photonic drive, a laser. You have a laser on your spacecraft. Maybe it's solar powered, whatever. You fire the laser, and as the photons leave the laser, your rocket gets a kick in the opposite direction. The only one that isn't that would be like a laser sail or a solar sail, where you've got some external propulsion source. The only one that wouldn't be would be like a laser sail or a solar sail, where you've got some external form of illumination that's firing the laser at your sail, and then the photons are bouncing off the sail, and that accelerates your rocket. But that only works while you're close to the laser. After a while, you're far away from your laser, and you're no longer getting propulsion. With transportation here on Earth, we have the idea of like a sailing ship, where the ship is out in the ocean and the wind is constant, pushing on the sail, and that allows it to have a constant form of propulsion. And there's nothing like that out in the universe, but the one idea that has been proposed is that you could harvest atoms of hydrogen that are floating out in the void, and then you could gather them together, crush them down, use them in a fusion drive to accelerate your spacecraft. And theoretically, that would work. The problem is that you would need to have a scoop that is sucking in hydrogen from the cosmic void that is like the distance from the Earth to the sun, like 100+ million kilometers long. Some kind of net, some kind of magnetic scoop that is bringing all this material in. The point is, probably not. There have been some ideas proposed that don't hold up to reality, like the EM drive or the Mach drive, but they don't seem to actually work in very pristine test conditions. It seems like the only way to move a spacecraft is to throw something out the back, and eventually you're going to run out of that thing that you're throwing out the back. So your follow-on question, DD, like the most efficient thing would be matter antimatter. If you could master matter antimatter propulsion, you could get close to a system that would take you across the Milky Way. Andrew G. Is it possible to travel in straight lines around the solar system, or do you have to travel in orbits? Could you just point your spacecraft straight at an object with enough thrust? I mean, you could theoretically fly in a straight line, but the place where you were trying to go might not be there anymore, and it's definitely not the most efficient way to do it. So think about this, right? The Earth is traveling around the sun at 30 kilometers per second. And if you want to fly to Mars, Mars is on a different orbit that is higher up, and it's actually moving a little more slowly than Earth is. And so if you want to get to Mars, you just launch off planet Earth, and now you're in orbit around the sun like Earth at 30 kilometers per second, and then you start to fire your thrust, and you raise your orbit so that you're now having an elliptical orbit around the sun where the line of your orbit crosses the Mars orbit, and you are able to then land on Mars when this intersection happens. And the cool thing about that is that you fire your rocket when you're in Earth orbit for a little while, and eventually this puts you on this new trajectory, and then you just stop firing your thruster, and now you just coast. So if you wanted to go in a straight line towards some target, you absolutely could. If fuel was no issue, then you could say, like, I want to go to Pluto. And then you just point your spacecraft at Pluto and you just start firing the thruster and firing the thruster. And Pluto just gets bigger and bigger and bigger. But all this time, you've been having to literally counteract all of the orbital motions are going on. It's incredibly inefficient, and we don't have any rocket systems that can handle it. So the only thing we can do is fire the rocket to put us on an orbit that intersects our target, and then we coast till we get there, and then we either enter the atmosphere or figure out a way to decelerate and go into orbit. It's all orbits, all the way down, wherever you go. Two galaxies rotating around a giant black hole have Lagrange points. So Tom, like I'm sure you're asking, your question's a joke, but you need one mass, one smaller mass, and like 1% of the mass, and then you need an object of negligible mass. So if you had a galaxy that was, say, 1 trillion solar masses, and it was being orbited by a supermassive black hole with 1 million solar masses, then there would be 5 Lagrange points between the galaxy and the black hole. But 2 galaxies rotating around a giant black hole, no. I mean, that's back to the, if you had the sun and you had Jupiter and Saturn orbiting around the sun, would those form Lagrange points? And the answer is no. Jupiter and the sun have Lagrange points, and Jupiter and Saturn have Lagrange points, but there isn't Lagrange points collecting them all together. Boom Confetti, how is it possible to watch your live streams later? You don't up them on YouTube, right? Well, the QAs are the live streams. When you become a patron, we link to the live stream that fed into the QA. So that maintains a link. But like, you're watching it right now. So just copy the URL somewhere, bookmark it, and then it'll be an unlisted video. So you can just watch it afterwards. But no, we unlist the live streams after they've happened because they're, it's duplicate content. It's very rough. They're longer. They're more casual. The Unrib. Fraser, after 40 years of learning about the universe, the more I learn, the more I'm blown away by the vast scale and mysteries unfolded. Do you feel the same? I'll do this question. All right. The Einrib. Fraser, after 40 years of learning about the universe, the more I learn, the more blown away I am by the vast scales and mysteries unfolding. Do you feel the same? I don't feel the same sense of awe and wonder thinking about the universe on a regular basis that I did a long time ago or when I was a kid or whatever. Like, there's these times when you get just overwhelmed by the vast scale of the universe, that we are this tiny planet orbiting in this relatively small solar system, that we are light years away from the nearest star system, that we are just one member of an island of stars with 100 plus billion stars, and that's just one of 2 trillion galaxies in the universe. The scales are mind-boggling, and what I feel blown away by is I feel sad a little bit that these parts of the universe I will never know. Some of them, most of them, 94% of the universe is inaccessible forever to us. It's only 6% of the universe that is even reachable. If we could just get going right now, go at the speed of light, we could reach some of these galaxies. The rest are too far away. And so there's so much universe, so many interesting things out there that we will never know. So that makes me feel, when I really sort of think about it, it definitely sort of gives me this existential dread, not dread. I just feel sad. I feel sad. There's like, I want to know everything. And I know that thanks to the laws of physics, there are parts of the universe that I will never know. But I find I'm so caught up now in the details. I'm so caught up in the day-to-day discoveries that are being made on so many different fronts, on galaxies at the edge of the observable universe, and the cosmic microwave background, and what's happening with gravitational waves and gravitational lensing and neutron stars and black, like all these things. They're all proceeding paper by paper as each one of the universe's secrets are being figured out, that it keeps me entertained, that it stops me from ruminating too deeply on the sort of vast scale of it all. So no, I don't feel that way anymore, but I know what you're talking about. And I think and I don't know whether you want to get rid of those feelings, because they're pretty great. I mean, this awe, AWE, right, is a wonderful feeling. It's it's the closest that I have to spirituality, is just this sense of awe, being in this universe. You don't want to lose that. But at the same time, knowledge has a way of chipping away at your awe and wonder and filling it with answers, and sometimes more questions. But I just find it fun now. And the more that I learn, the more questions I have, and the more fun that becomes. So it's phase. It's a phase you're going through, and you'll come out the other side of it. Sorry, just looking for a question. What time are we at? All right, probably like one more. So Alexis Omnis, does superposition happen because the particles are connected to each other through higher spatial dimensions? And can particles be entangled through time? We don't know. Nobody knows how. I mean, in some cases, like, we just observe these things, but we don't know why these things. That's a trickier question. Right. Waka Waka. What do you think astronomy will look like in 100 years? We have no idea how much better astronomy is going to get in 100 years. I mean, look at computers. Like, imagine going back on 1922 and asking, going to a room full of mathematicians and going, like, what will computers look like in 100 years from now? And like, at that point, computers were people who would sit and do math for you to calculate the trajectories of artillery shells. And after a while, they figured out computers. I mean, whenever you get these exponential curves, our minds are incapable of comprehending how dramatic the changes will be. There's been a few papers that I've seen that have started to think about this. The one that I really liked was someone was saying, how many exoplanets we know about by 2050? And they just took the rate of planetary discoveries and then charted that. They just took the rate of planetary discoveries and then charted that over the course of the coming decades, and figured that by the year, say 2050, we will know of around 100 million exoplanets. When right now we know 5,000, because that's how exponential growth curves. And like, maybe it won't be 2050, it'll be 2060. And then of those, we will have categorized the atmospheres of millions of planets. We will know with precision. And we could very well have much more powerful telescopes, like the quantum telescopes that I mentioned in my interview with Lee Feinberg. We could have the solar gravitational lens telescopes that's operating out at 1,000 astronomical units from the sun. Each one of those could be giving us a megapixel scale image of a terrestrial planet orbiting around a sun-like star. We could have enormous space-based telescopes built, maybe one that is 5 kilometers across. Maybe we have one at each of the L4, L5, and L3 Lagrange points to form a giant equilateral triangle, an interferometer of these telescopes working together to make a telescope that is virtually 300 million kilometers across. What could we see with that? We will have these surveys that are going to be scanning the sky on a regular basis. We will have computers capable of crunching this data and searching for all kinds of interesting things. It boggles the brain on what we will be capable of in 100 years, but it will be a lot. And it's funny when you think about, like, should we be worried about sending out signals into space? If we've gone from zero to this level of astronomical discovery already, and where we're going to be in the coming future, just imagine some alien civilization that's had 1,000 years ahead of us, 10,000 years ahead of us, 1,000,000 years ahead of us. Think about what their telescopes look like. They know we're here, and hopefully soon we'll find them too. Okay, so I'm going to do the exit stuff, and then I'll stick around for some overtime. So don't go anywhere. It's not over yet. If you like my answers to your questions, as well as other things that we do at Universe Today, consider joining our Patreon club. You'll get an ad-free experience on universetoday.com for life, even if you unsubscribe. You get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who's already subscribed, and welcome to the newcomers: Clive Walker, Leonard Jackson, Gary Schroeder, Herb Helbig, Priscilla E. Richardson, Puppy Space, Pratap Prumali, Jonathan Sasson, Dennis L. Taylor, Alex Lippert. Join the club at patreon.com/universetoday. All right, those are all the questions that we had this week. If you're still watching, don't forget to vote. Pick the planet name for the one that you like the best. And remember, we record this show every Monday at 5 p.m. Pacific time right here on my YouTube channel. So come, join us. All right, we'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us. Okay, I'm going to do the intro, Chad. So let me see what the questions were, and then let me... Okay. How would the constellations change as we move through space? Can we see closer to the edge of the observable universe? Why didn't we get heavier elements after the Big Bang? All this and more in this week's question show. Okay. All right, I'm going to stop the recording. I'll stop that. And then, Chad, if you want to book out, I will. I'll grab some questions just straight out of the chat. So, and if you want to stick around, you can. So I'll go backwards. Tom's Cubes. Who will walk on Mars first? Tesla bot or Neuralink monkey? Man, good question. Um, Scientists photographed photons being both waves and particles, but in the photon, the particles look like separate from the waves. Can you explain what looks like that? No, that's beyond my um, pay grade, pay range. I'm not a physicist. I am a journalist. CJ Dubs, do we know what the poles of the sun look like? Are there plans for a polar solar orbiter? The solar orbiter kind of is a polar orbiter. So I will. So the solar orbiter. This is the European Space Agency spacecraft, and it is changing its inclination, and eventually they'll get to a point where it can actually see the poles of the sun. There's no plans to do anything that's going to be more like higher angle than that, but like spacecraft really last longer than you're expecting, and so just orbit after orbit just keep getting higher and higher and higher. And I wouldn't be surprised if 20 years from now, solar orbiter is right over the poles of the sun. I can see your question, Patrick. Let me see. But I might not be able to answer it. Could the orbital speed of stars around their supermassive black hole found by Vera Rubin potentially be explained by stronger mass-based time dilation in the center of galaxies than their edges? So Vera Rubin won't be able to find stars orbiting supermassive black holes because they're enshrouded by dust. You need an infrared observatory to be able to find that. Would the speed be... I don't really understand the question. Would the orbital speed be changed by the more of the time dilation? They're too far away. Like stars that are orbiting around black holes are way too far away to experience anything, any kind of significant time dilation. You have to get really close, like a few million kilometers away from the black hole for the time dilation to get serious. It is what it is. Will Webb end up helping figure out the theory of everything? I don't think so. No, it's not a theory of everything kind of instrument. Like it's able to observe galaxies at very high redshifts. It's able to see exoplanet atmospheres, but it is definitely not a. It's definitely not a. Like where would we get it? Like the theory of everything, what you're really trying to do is you're trying to merge gravity and quantum mechanics. You're trying to make those two theories talk to each other. And right now they don't, right? You put gravity into quantum mechanics and you get nonsense. You put quantum mechanics into gravity, you get nonsense. And so you need some theory of quantum gravity. And like maybe if there are predictions made by quantum gravity that could be seen at a vast cosmological scale, then James Webb might be able to help in discovering it. But Tropical Tom Garcia, are any of the cubes from Artemis working still? Half of them. Half of them died. Half of them are working. Google account. Would you rather time travel to the past or the future? The future. David Bertram, who's on next on the list for the full interview? I had an interview, but I had to cancel it because my power went out. So my next interview isn't for a while. I've got to get an interview going actually. So the 19th is my next interview that's scheduled. But often I'll ask people if I can interview them, and they'll say yes. There's a few people who I'm sure I can talk to pretty quickly. I don't want to get them to interview them. So stay tuned. I'm sure something will come out. Kevin Sullivan, could a moon affect a woman's menopause? No. We did a video about this, like why do we go crazy during the full moon? And the answer is that we don't. That many studies have been done about the effect of the full moon, and there is no effect. There's purely placebo. So no matter what it is that you're proposing, it has no effect on anything. Full moon does not make people go crazy. And people always will like then give anecdotes like, I saw, I used to work at a hospital and every time there was a full moon, we would fill up. I'm like, I'll bet you that's not true. I'll bet you if you actually went back and looked through your records that the place did not fill up. It's just the placebo effect. It's coincidence or the observer, like you're noticing. Like, when you notice something and then suddenly you notice a thing all the time. What do they call that? The observer effect? I forget what it's called. I don't know. My ex turned into a werewolf every time. Well, yeah. I mean, we know that the full moon causes lycanthropy, so that's no question. Ivo Barros, does gravity have infinite range? Is there some Planck limit to its range? There's no limit. The gravity moves at the speed of light, so there's no range to it. But are you wondering? I mean, is it quantized? I don't think we know. Bader-Meinhof effect. There you go. All right, let me take a couple more questions and then I'm going to go eat food. Brent Hine, why do meteorites falling onto the moon's surface leave around craters as if they all drop straight down? That's a great question. So when an object that's moving really fast, like kilometers per second, crashes into the moon, it vaporizes, and the energy is released at the moment that it strikes the target, and it's like an atomic bomb, like a nuclear explosion that goes off. So no matter what angle that the rock is coming in at, it will, like, say you've got like the moon and the rock comes in at a very low angle. The second it hits the lunar surface, it stops, detonates, and you would get this mushroom cloud coming out of the moon perpendicular to the center of the moon. And they always make circles no matter what angle. You'd expect them to like furrow in, but it's not like the thing is crashing into the moon and bouncing along for a little bit. You get a couple of situations where an object will get really close to the moon and it'll be torn up by tidal forces, and then you can see what looks like kind of like a machine gun pattern of craters, and you know that that's because the asteroid broke up moments before it hit. But in all cases, they are you get this circular explosion just because the second it hits the moon, and no matter what angle, it now just creates this enormous explosion. Basket of puppies. How big can a planet get before it starts becoming a gas planet? Well, it's what it's made out of, right? So a gas giant is going to be made out of gas, of hydrogen and helium. So the smallest gas giant that I think we know of is at about 1.5 times the mass of the Earth. But that's about it. There you go. Confirmation bias. That's it. You notice what confirms your ideas. Dustman, which movie is better, Deep Impact or Armageddon? Deep Impact by like 1,000 times. Armageddon is so bad, and Deep Impact is pretty good. All right, I'm going to wrap up, but I'm going to leave you on this. Was Andor the best Star Wars media created in the history of Star Wars? All right. Thanks, everyone. Now you're going to be like, oh, you really want to talk about it, but the live stream is over. All right. I will see you all next week. Thanks, everyone. Oh, and thank you, everybody. Thanks to all the moderators. Thanks, Chad, for stepping in for Nancy this week. Thanks for everyone watching. All right, we'll see you later.